We're going to start looking at chemical reactions, and we'll start with net ionic reactions, in part because of this first learning objective, which is to be able to identify reactions as acid-base, oxidation reduction, or precipitation. Those are the only three types of reactions that the College Board will ask you to identify. The associated essential knowledge that we need is that precipitation reactions often involve mixing ions to form an insoluble or only slightly soluble compound. We also need to know that sodium, potassium, ammonium, and nitrates are always soluble. The second learning objective is to be able to write balanced chemical or net ionic equations if we have information about a physical process, if we have information about reactants and products, or ions for a chemical reaction. 3 pieces of essential knowledge go with that. All physical and chemical processes can be represented this way. Chemical equations represent chemical changes and must show the conservation of mass. And then balanced molecular, complete ionic, and net ionic equations have different symbolic forms and are used for different purposes. Let's start by thinking about representing a physical process, something like boiling water. We'll start by representing liquid water. So H2O as a liquid, that little L represents liquid, and we're going to turn it into water vapor, H2O, as a gas. The L and the G represent the phase of matter, but the chemical composition, water, remains the same. So a couple of things to notice, right? One, the formula has not changed. Only the phase changes. This is what makes it a physical process. The chemical composition hasn't changed. The bonds don't change. The ratio of hydrogens to oxygens and the way they're arranged and bonded hasn't changed. Another physical process is dissolving magnesium chloride. So if we take magnesium chloride as a solid, we could dissolve this and get magnesium chloride that is aqueous. So again, the only thing that's changing are the symbols that are showing us the state of matter. So we've got that same thing. The number one, the formula is not changing. And number two, the phase symbols are what's changing. We could also write it like this though. Because remember that what really happens when an ionic compound dissolves is that the ions dissociate. So we really get these two independent ions now floating around in the water. So we could write it like this, and this kind of makes it look like we now have changed the chemical composition. But really, magnesium chloride was already magnesium ions and chloride ions. That's already what we had. Just by convention, when they're a solid, we don't write these because they're canceling out. So when we write AQ like this just means that this is what has happened. So this, writing AQ like this, is just shorthand for this. You'll actually see it either way. When we see it written in this long form like this, sometimes this can trick us and make us think that this is a chemical reaction, that something has fundamentally changed. But in fact, it has not. We've still just got these ions. They were close together as a solid, and now they are spread apart. So on the left, where we've written it as a solid, we've got magnesium and chloride really close together as ions. And on the right, where we've got it dissociated, we've got magnesium and chloride as ions, but separated apart, but still as ions. So nothing has really fundamentally changed. We've got the same proportions. They're both in ionic forms. They both have the same number of electrons that they started out with. They haven't exchanged those. The ions have not changed. The electrons have not changed. They're the same on both sides. We've just represented them a little bit differently because of how close or far apart they are, which is really the same as up here with water. Up here, the liquid was very close together. The water molecules were very close together, and in the gas, they were farther apart. We're more accustomed to seeing equations with chemical reactions where we have reactants on one side and products on the other, and the two sides have very different formulas. So we've got different formulas on each side. But we want to note that we have the same atoms, that we have conserved the mass. And we do that by balancing the equation, remember, with the coefficients. So that's why we have these big coefficients out in front of some of the formulas. Let's look at the example down below and we will balance this equation together. We always want to start by just counting what we have on each side. So on this side, I have 3 calciums. Polyatomic ions, I like to count as an entity. So I have 2 phosphates, 3 hydrogens, and then I have another phosphate over there. So I've got a total of 3 phosphates. In my products, I've got 1 calcium. My phosphate, I have 2. And hydrogens, I have 2 times 2 is 4. Let's start with my calciums. If I put a 3 here, then I have 3 calciums. 3 times 2 gives me 6 phosphates. And 3 times 2 is 6 times 2 is 12 hydrogens. So if I need 12 hydrogens on my reactant side, I would need to put a 4 here. 4 times 3 is 12. And that means I would have 4 phosphates plus these 2 from the calcium phosphate would give me 6 phosphates. So that was just a quick little review of equations, balancing equations from Chem 1. If you need more practice with that, there's loads of stuff linked in the outline. When we're talking about net ionic equations, we're mostly talking about that specific kind of precipitation reaction, which is a double replacement reaction. We talked a lot about this in Chem 1 too. A double replacement reaction usually occurs when we have 2 soluble ionic compounds, so 2 things that are aqueous, and when we put them together and let them react, our reactants end up, one of them is aqueous, but one of them is not. One of them forms a solid product, and that solid product is the precipitate. And the reason we can write a net ionic equation is because notice that some of these ions, really nothing happened to them. If we look at our original reactants, notice that these green ions, they never changed. They just stayed green ions. And the same thing with these little purpley pink ions. Nothing ever happened with them. They were just ions in the beginning floating around in their little beakers, and they stayed little ions floating around in that end beaker. The only thing that experienced a change were these red and blue ions, which formed a new compound, the silver chloride. So that is really the thing we're interested in. That's really where our change happened. These green and pink ions are really what we call spectator ions. And so sometimes, since that's not really where our change happens, we just want to drop them out of the equation. When we do that, we get the net ionic equation. So we can represent this 3 ways. We can represent this as a molecular equation, which is really what this is. We started with silver nitrate, so we write that whole formula out, and it was aqueous, and we let it react with silver chloride, again, write the whole thing out, aqueous, and we ended up with sodium nitrate, which was aqueous, and silver chloride, which was solid. So we write everything out in its ionic formula and put the little AQ or S symbols behind it to indicate if it's aqueous or if it's a solid. But we know that if it's aqueous, that means that it's really dissociating. So all of these things are really dissociating. So we've really got a silver ion and a nitrate ion, a sodium ion and a chloride ion, a sodium ion in the product and a nitrate ion in the product. This silver chloride, though, is staying together as a chunk. It's a solid, so those things are not ions. So we can take that, all of those dissociated bits, and write them out as individual ions. That's where the total ionic equation comes from. We've got a silver ion and a nitrate ion and a sodium ion and a chloride ion. That's our reactant, all those individual ions, and we pour them all together. And then in our product, we still had a sodium ion and a nitrate ion, but our silver and chloride ions formed a solid. So that's our total ionic equation, and we get it just from looking at our molecular equation and those states of matter symbols. If we look at that total ionic equation, we can see which substances, which species didn't change at all. And I noticed that sodium didn't change at all. It stayed an ion on both sides. I noticed that nitrate, didn't change at all. It stayed the same on both sides. Those are my spectator ions. If I want to write a net ionic equation, then I can drop those out of the equation. I know it's on the next page, but I'm going to squeeze it in here real quick and then I'll write it again. The net ionic equation would not include spectator ions. So it would be my silver ion and my chloride ion forming that silver chloride solid. And that would be the net ionic. It wouldn't include the spectator ions because that's not really where the change happened. Right? So I'm going from that whole total ionic equation, taking out my spectators. That's how I'm getting to the net ionic equation. And the net ionic equation lets me really focus on where the changes happen. A couple of things to keep in mind. One, this never includes spectators. We can sometimes see this in a molecular equation. We don't always have to have the total ionic equation because any ion with AQ behind it on both sides of the equation will be a spectator. So sometimes we can see this from the molecular. You just have to be a little bit careful as you look at it. Let's look at another example here. Here we've got copper chloride and barium hydroxide, and we're letting those two things react to form copper hydroxide and barium chloride. Let's practice trying to find the spectator ions before we even do the total ionic. So if I'm looking at copper, here's my copper and here's my copper. Does copper have an AQ behind it on both sides? Over in my reactants, it does, but in my products, there's a solid behind it, so no. So that's not going to be a spectator ion. If I look at chloride, chloride's here and then chloride's here. Does chloride have an AQ behind it on both sides? In my reactants, it does, and in my products, it does. So chloride is probably going to be a spectator. Barium, AQ, yes, but in my products, oh, yes. So barium also might be a spectator ion. Hydroxide, in my reactants, yes. In my products, oh, no. So barium is probably not going to be a spectator ion. So already, without even doing the total ionic equation, I'm starting to see that these are going to be my spectator ions. So what I'm probably going to be focused on in my net ionic are these copper and hydroxide ions. Let's go ahead and do the total ionic equation though, just for practice. I'm going to erase some of my scribbling here just so we can see clearly. When you're writing the total or net ionic equation, you've got to be careful of the charges and the coefficients. Okay, so every ion needs a charge on it But you also need to make sure that you've got the right coefficients. So copper and chlorine are both going to dissociate because they are aqueous. So what's the charge on that copper ion? Well, it's a transition metal, so I'm not sure from the periodic table. But because there's a 2 behind that chlorine, I know that it's going to be a +2. Chlorine, I know from the periodic table that it is a -1. Because there's a 2 behind it, I know I'm going to have 2 of those chlorine ions. So I need to have a 2 coefficient. Barium hydroxide is also going to dissociate. Barium from the periodic table, I know is a +2. Hydroxide is a polyatomic that I know is a -1, and there's a 2 behind it, so I've got to make it a 2 coefficient with a -1 charge. Here's my solid, so I don't need to dissociate that one. Copper hydroxide does not dissociate, but barium chloride is aqueous, so it does. Barium is still a +2, and chlorine is still a -1, and this 2 behind it tells me I have 2 of them. Now this is already balanced. 1 copper, 1 copper. 2 chlorines, 2 chlorines. 1 barium, 1 barium. 2 hydroxides, 2 hydroxides. If you've done it correctly, it should be balanced, but always check because it's a good way to find if you've accidentally overlooked a coefficient or a charge. Your charges should balance on both sides. Your charges on ions should be the same on both sides. Everything should be balanced. So that's a good way to double check yourself to make sure you haven't overlooked something. Okay, now let's just find our spectator ions from our total ionic equation. So barium is an ion on both sides. Chlorine is an ion on both sides. So our spectator ions are barium. Anytime you're talking about an ion, you need to have a charge on it. And chlorine, which means our net ionic equation won't include those two things. Copper plus 2 hydroxides gives us copper hydroxide. That's our net ionic equation. So here are some things to keep in mind. These are ions that our essential knowledge told us were always soluble. That means they're always going to be spectator ions. Anything that is always soluble is going to be a spectator ion all of the time. So anytime you see any of these things, you know they're going to be a spectator ion. Let's do just a little bit of practice writing some net ionic equations. And we can try to do this without going through the total ionic equation first. So I'm looking at silver here. Silver is aqueous. Is it also aqueous in my product? No. It's a solid in my product, so I'm going to leave that alone. What about nitrate? Well, nitrate's one of my 4 that I know is always going to be a spectator ion. So I can kind of just cancel that one out. I can see it is aqueous in both sides, but I know it from the list of 4. Sodium, what about sodium? Sodium's also in my list of 4, so it's probably going to be a spectator ion. And I see that it is in fact aqueous on both sides. So I'm going to be focused on my silver and my sulfate forming silver sulfate. So I'm going to have 2 silver ions. Now what's the charge on that silver ion? Silver's a transition metal, but I know nitrate's a -1. If I have only 1 silver ion and 1 nitrate ion, then that silver ion must be a +1. And sulfate, SO4 is a -2. And that makes sense because over here, I've got Ag2SO4 as my solid. 2 silver ions and 1 sulfate ion, 2 +1s and a -2. All right, let's look at this one. So this next one is a single replacement reaction, which means it looks a little bit different. But I can still write a net ionic equation because I still have a spectator ion. I just have to find it. Is it SC? No, it's not, because that's the solid on the reactant side. Is it AG? No, it's not, because that's the solid on the product side. Is it NO3? It is, because that is aqueous on both sides, and we know that nitrate usually is a spectator ion. So that's what's going to drop out, and I'm going to have my solid for my reactant side plus 3 silver ions gives me 3 silver solid atoms, and here I've just got 1 Sc. What do you think that charge should be? I know that nitrate's a -1, and look, I'm going to have 3 of them over here. That tells me that this must be a +3 charge. Here we've got calcium carbonate and hydrochloric acid forming calcium chloride, carbon dioxide, and water. So again, this is a little bit different because it's not a double replacement reaction. But we can still write a net ionic equation. We just need to find our spectator ions. We know it's not calcium. We know it's not carbonate because those start out as solids in our reactant. So right away, those can't be spectators. What about hydrogen? Hydrogen's aqueous in the reactant. Is it in the product? No, it's part of the liquid, so not aqueous. What about chlorine? Chlorine is aqueous in the reactant. Is it in the product? Yes. So we can eliminate chlorine from both sides. So our net ionic equation would be calcium carbonate plus 2 hydrogen ions gives us calcium ions plus carbon dioxide and water. So even though the only kinds of reactions you'll be asked to classify are precipitate reactions, acid-base reactions, and redox reactions, which we'll talk about later, you might be asked to write a net ionic reaction for a reaction that falls outside of one of those categories. You can write net ionic reactions for lots of different kinds of reactions. The key is just to find your spectator ions and remove them. And that process is the same no matter what type of reaction it is. Let's look at another thing to keep in mind about net ionic equations. And that is sometimes you're given a net ionic equation. How do we know it's a net ionic equation? They don't tell us, but notice all these ions. It's very likely a net ionic equation. And then notice that a lot of these compounds that they're using contain the same ions bonded to nitrate. And nitrate is, we know, usually a spectator ion. So just keep that in mind that this nitrate is probably a spectator ion. So these copper and gold ions are probably the copper and gold ions in this equation. So just kind of keep that in mind as you start trying to tackle these FRQs.